Next guest speaker is Ellen Roche from MIT, who is reinventing cardiac care. Welcome.
Hi, good afternoon, everybody. Sorry, it's late on a Friday, so I'm probably keeping you from your weekend, but it's a privilege to be here to talk to you all today in such a beautiful setting. It's gorgeous. Okay, so I'm going to talk to you very briefly today, just for 10 minutes, about some of our work that we do in the lab right across here in E25. We work on devices for augmenting and repairing the heart. So just kind of a background to my research, I'm interested in dynamic organs, specifically the heart and the lungs, and these organs are in constant motion, and they have complex tissue architecture, which lends them very composite mechanical properties. And this represents a challenge when we're trying to repair these organs when their function becomes impaired. We love a challenge here. So in my group, I started here as an assistant professor in 2017 and now an associate professor, and I have a joint appointment between mechanical engineering and IMS, the Institute for Medical Engineering and Science. And we're using dynamic actuation and soft robotic techniques to augment organ function. We design bioactive implants, and we look at ways we can modulate the immune response to implanted devices. And we also use the same soft robotic approaches to develop high-fidelity test beds for testing these devices on the bench before moving to preclinical studies. We use a lot of tools to do this research. We use a deep understanding of pathology and physiological biomechanics. We use advanced imaging approaches, so we partner with groups at MGH, at the Martino Centers. Here's an example of diffusion tensor imaging MRI. We use computational models, finite element and fluid dynamic models. And we use advanced materials and robotic approaches to do so. I often break my research down into these 4 areas: augmenting organ function at the organ scale, locally repairing tissue defects, developing simulators using tissue and synthetic materials for enhanced testing, and then computational models. Today, the time is short, so I'm just going to focus on one example where we do local repair or replacement of focal deficits. And I'm going to talk to you about one device we're working on, we're really excited about working on and trying to spin out of the lab. This is a device for stroke prevention in a subpopulation of patients that have non-valvular atrial fibrillation and that are ineligible for blood thinners and at risk of stroke. Our technology is a medical device. It uses a biopolymeric scaffold to occlude an outpouching in the heart that's called the left atrial appendage. And the scaffold encourages tissue ingrowth once it's implanted. So this is a schematic of a normal heartbeat, but the rhythm of the heart can go into disarray. And one example of this is atrial fibrillation. Atrial fibrillation is when the atria, or the upper chambers of the heart, quiver, so they're moving really quickly. And this is a condition that affects a huge number of people, so over 38 million people worldwide, and 1 in 10 of those over 65 suffer from AFib, which is a huge number, and it costs a significant amount to the US healthcare system. And this condition causes blood clots, because if the atria of the heart are moving so quickly, the blood can become stagnant and clot. And the blood clots can travel to the brain in the vessels, and when they're at the brain, they cause a stroke. And people with atrial fibrillation are at a 5-fold risk of stroke. And 90% of the clots that form in a thumb-shaped outpouching of the heart that's called the left atrial appendage. Treatment options for stopping this from occurring include pharmacological methods with blood thinners and electrical methods, but neither of these is completely ideal, and both have their own problems. So one way to think about stopping this from happening is very simple: to just block this appendage that's coming off the side of one of the chambers of the heart. This would be a one-time procedure, and it wouldn't require the patient to be on long-term blood thinners or anticoagulants. And And you can do this in a number of ways. Surgically, you can do it by clamping the outside of the heart or suturing it closed. You can also do it through a catheter or a long tube that goes into the leg and minimally invasively close it off. You can do that from the outside or the inside of the heart. But for multiple reasons for patient benefit, including length of stay in the hospital, the invasiveness of the procedure, the need for long-term blood thinners, and the number of devices required, internal occlusion with a catheter makes the most sense. And a lot of companies are doing this, but there's this issue of fitting a square peg into a round hole. And the reason that we talk about this mismatch is because all the current occluders for the LAA look like this. So you can see they're all made of metal and nitinol shape memory alloy with some sort of polymer. But what you also notice about them all is that they're round. And if you think then about the number of LAAs that are round, it's only 5.6% of us that have a round neck to the LAA. Also, the sizing, there's a mismatch. So these devices cover the size from 16 to 33 millimeters, but the range of sizes in reality is 10 to 40. And the LAA is a very complex structure. So beside it, there's a circumflex artery and there's a mitral valve, both of which are very delicate but critical to heart function. And it's also very heterogeneous. So you can see the absurd names that we use to categorize the LAA, everything from chicken wing to cactus to cauliflower. And you can see how some of the lobes can be doubled and it can be cone-shaped, so really different in all of us. But because of this heterogeneity, patients are often excluded from treatment with a catheter. And often when they are treated, the devices can be mismatched. And if they're not accurately sized to the patient, you can get erosion or you can get leakage. And you can actually get a device-related thrombus, so you can get clotting from the device. So there's a clinical need for a single minimally invasive solution that is useful for all patients. And that's what we're working on. So this is a catheter that would be threaded up from the leg, so an incision in the groin. It would go up to the heart. And this is what's called transeptal crossing. So the catheter goes across the septum of the heart. And this is something that's currently done commonly with interventional cardiologists, so not a new paradigm. What is new about our technology is this part. So when you get to the left atrial appendage, we inject these microgels into a collagen casing. These are alginate microgels, biopolymer, and they fill the casing and occupy whatever shape of LAA is present. And then that acts as a scaffold for tissue to grow over it. So in the end, there's just tissue scaffold covering this occluder from the bloodstream, patient's own tissue. This is enabled by shear thinning material. So these are granular hydrogels. When you deliver them through a catheter, they're shear thinning, they go really easily, and when they come out, they solidify and they stabilize. So when you inject these into a casing, they can accommodate any anatomy and form a stable plug and act as a scaffold for tissue infiltration. We can do this in any orientation, so this just shows arbitrary 3D printed shapes, and you can see that we can fill them in any orientation, even against gravity, and keep them in place. We can also do secondary sealing if we need to seal it off from the bloodstream, and they can maintain their solid location and be stable under fluid. Here you can see us filling a silicone left atrial appendage in a cardiac model in the lab, and you can see how the technology is adjustable and accommodates any anatomy. You can also visualize this on X-ray, so this is on fluoroscopy, and you can see the dark part there is where we're filling the LAA. This is significant for patients because if we can visualize it on X-ray, we don't need an additional probe down the esophagus that's currently used for imaging. So multiple benefits for the patient. It expands the treatable population. There's no post-procedural blood thinners. No leakage around the device. You only need one device to do it. And there's no tissue damage or erosion because the stiffness matches that of tissue. For the healthcare system, potentially this can transform LAO occlusion into a one-day outpatient procedure even, without requiring general anesthesia, without requiring a probe down the esophagus. And there's not much retraining for the interventionalists because they're familiar with the paradigm of transeptal crossing. We can expand this portfolio beyond the heart, so we can think of number of locations in the body where there's three-dimensional tissue defects that need to be filled. Basically, this can be a platform where we deliver these building blocks or inside a catheter for biofabrication. Some of these outside of the atrial appendage include cerebral aneurysms in the brain, obstetric fistula, and GI diverticula, and we have a number of projects ongoing in the lab based on this. We can also do multi-material embedded biofabrication, and this is in collaboration with Jennifer Lewis's lab at Harvard, where we can embed one material inside another. So you could imagine a pharmacological agent or a biologic delivering it inside for therapy. So this embedded printing works really well, and you can still achieve that solidified structure at the end. You can get really high fidelity with these prints, so you could think of an in situ bioprinter. And you can maintain any shape inside the embedded solid as well. So you could imagine depots of drugs or biologics for various applications. We can also guide this with a magnet, an external magnet, if we want to achieve high fidelity in situ 3D printing. And that's something that we're working on further to develop in the lab. Here's some examples of the preliminary prototypes where we're printing in targeted locations. And here we can use light to photopolymerize as a secondary way of stabilizing if we need to in the LAA. I'll finish by mentioning, sorry, I'm not sure what that is. I'll finish by mentioning that we do need to develop high fidelity test models to test all this. So behind that mute sign, there is multiple LAA models that we develop in the lab, and we print and cast to be patient specific, so we can really test this technology on the bench. We also have a whole flow loop set up. This is better, and we can have modular replacement of the left atrial appendage. So we can take any of us here, do a quick scan, and then print a mold to cast the actual geometry of any of our left atrial appendages, and then attach it to the flow loop and subject it to physiological flows and pressures so that we can do a very realistic representative testing and size devices accordingly before we would do it in a person. And we really believe that this paradigm can be adopted for multiple technologies as well. I'll leave it at that and thank the team. This is a multidisciplinary collaborative team with my graduate students, Keegan and Connor, in collaboration with Jennifer Lewis at Harvard, Dee Dee Wong, who's an interventional cardiologist, and we get advice from Alan Will on the entrepreneurial and innovation side. Thanks for having me today, and sorry if I went a little bit over. I appreciate it. Thank you.